All right, so now we will officially introduce the design of HDFS and MapReduce. Okay, so first of all is the storage system, the distributed file system. It's called HDFS, right? A short name for Hadoop Distributed File System. And we need a first distributed file system at first because foremost, right? Because the data must be stored, right? And um, because of the data volume, so it is impossible to store the data on a single node. And so we need a distributed file system so we can have multiple data, multiple disk drives to store the data. And as you can see, when people design this file system, is thinking about the scale of more than 10,000 nodes, more than 100 million files, and more than 10 petabytes of files. So it is a huge amount that can only be handled by a distributed file system, right? And in the reason, and if you have a distributed file system, actually it's not hard to handle such a volume because we could store the file on different nodes. We could even partition the files on different nodes. So if you have more nodes, you can store more data. And the reason we want to partition the file is because we can explore parallel I/O, right? That's exactly what we talk about when we introduce the MPI/I/O. Exactly the same concept, right? So the key here is to even partition the files across multiple nodes. Okay. The second thing is we have to ensure the data reliability, right? We cannot have a data loss. And we want to ensure that while using the commodity hardware, means the hardware that can be bought by anyone in any computer regular shops, okay? Just like the hard drive you could buy from a computer shop, okay? And so in order to do that, those commodity hardware implies how value is common. Especially you have so many machines, so many disks, then the probability have a failed disk, failed drive in the system is almost 100%. Okay, so the best way to do that, to overcome that, is to replicate your file, right? Replicate your data across multiple machines. So the probability have, say, 3 machines or 3 drives fail at the same time will be much, much smaller, right? So that's why the data will be partitioned and will be replicated on those storage nodes. Okay? And finally, in order to ensure the throughput of your file system, so the API, the read-write operation provided by these file systems are actually customized and limited. It is not like the what we call the proxy file system, right? Proxy file system is the file system interface that is commonly support. It's actually become a standard for Linux file system, right? So for any for the regular local file system, usually it will provide the API follow the proxy interface. So for example, you could read write right any bytes from a file right at any place at any time from a normal regular local file system. But for HDFS, it is not the case. As you can see, it only supports append, but not random write. So you cannot just jump your position around the file and try to override some of the content from some part of the file. It is not even allowed, and it's not provided. The API is not provided by the HDFS. Okay, so that means you have to go through the API, the interface, define and implemented by the HDFS. instead of just through the regular file system, system code. Okay, and the reason for that is because of the performance, the throughput. Okay, um, as you can imagine, why random write is not supported. The reason is if you want to support random write, you will encounter the data consistency problem, right? Means if you concurrently write some file, then you have to make sure the ordering of this writing behavior between processes or even between other client servers, okay, client nodes, okay? So you will require some communication. You will require some global locking mechanism. So that will make the solution unscalable. If we have, if we are talking about thousands of clients try to access the same file at the same time, then a global lock will drag down the whole performance. Okay, so you can see it eliminate the behavior, the the operation on this file system, so that it can avoid some of the locking mechanism and make sure the system can always working at very high IO throughput without too much synchronization and communication overhead. Okay? So this limitation actually means that the file system is designed for a specific type of application. Okay, so this because it target on those large and sequential data processing. Because for those processing, for sequential processing, you don't have random behavior, right? Random access behavior. So it's okay not to provide a random access API for the application. Okay. And this type of application actually is very common and the majority of the application from big data, right? Because if you are talking about a big data solution, you usually have a huge amount of data, and all you want to do is to scan through the data and while analyze the data, right? So you will, and also you usually just read the data, right? You don't want to override the data, right? Because you only want to process the data that you are, you collected. Okay, so you don't want to drop the data, you don't want to modify the data. Those are the raw data you want to keep. So that's why generally you don't need random write at all. Okay. Okay, so you can see this is not a regular file system. It is a customized file system for solving big data problem, for big data application. Okay, okay. Now we look at a little bit detail about the architecture of this distributed file system. Okay, so you can have a little bit idea about how a design of a distributed system will look like. And this design you can see again in almost all the distributed system, including MapReduce or Edge-based, all the other solution we mentioned. They are all very similar, as you will find out. Okay. So for HDFS, the architecture is quite simple. It's a master-slave architecture. Means that you have a master node to control everything, and you have unlimited or a huge number of worker or slaves to do the real work. The master just the control node, and the slave, the worker, is the one to do the job. Okay, and so here, because this is a file system, so that means the slave over here is called the chunk server. So the chunk server is a regular server. Any server that you install with a Linux OS is just a regular server. Okay, and so a regular server, of course, you have file system, right? You have local file system. So so that means it can use to store the data. Okay, so what happened is, as we mentioned, a global file, right? A file, right, that viewed by the application, by the client, will actually be partitioned and replicated and into those data chunk. And each of data chunk is stored as a file format, is in the form of a file on the local file system of those chunk server. Okay, so so as you can imagine, a file will be partitioned, and if we want to read data from a particular position, or we want to operate on that file, we might still need to know the how to reconstruct the file back, right? So those information are called the metadata. So the metadata are the data that describe the file content, including the position of the file or the chunk size of the partition. Okay, all those information are stored at the master. Okay, so what happened is we can see we'll separate the control flow and the data flow. The control flow means the control message. So the client, when he try to read or write or open the file, he will first query the master and use those metadata information to know which chunk server it needs to talk to or try to retrieve the data. And it can retrieve the data or get the data directly from the chunk server without going through the master. So the data path is directly between the client and the chunk server, while the control plane, the control information is communicated directly between the client and the master. Okay, all right. And the master, of course, also need to do many other management work. For example, he needs to know whether a server is is malfunction or is dead or is offline, right? Because fail is a norm in distributed system. So so the master needs to know when a server is is failed, and when it's failed, the master has the responsibility to copy the data from his one of the server to another place, because remember every data is replicated 3 times. So even so one of the servers down, you should still have 2 copy exist, right? So you can access the data from one of the replica and create another third replica on one of the chunk server that is still working or alive. Okay. So in order to know that whether a server is failed, it needs at least you use the heartbeat message to know that. So between the server and the worker, it will periodically, the master will ping the server, will ping the chunk server, the worker, to know whether it is alive. Okay, and if it doesn't receive any response, then he will trigger the recovery steps. Okay. Okay. Here you can see more clearly, right? In terms of from the user point of view, what he view is a file with a huge file size, and the chunk size in the distributed system is usually is a fixed size chunk. The size is chunk size is fixed at the 64 megabytes. Okay. And so now if you have a 84 megabytes file, then you will be partitioned into 2 chunks, and also it will be replicated, for example, 2 places in the system. So you can see here you have chunk 1 on each of the chunk server. Okay, and chunk 1, chunk 2 will be stored as a separate file on those local file systems. Okay, all right. And so if you want to read the data from a certain position of the file, you have to first ask the server, right? The metadata server. So the metadata server will let you know what's the local file name for storing your data, and what position you should start reading from. Okay. Okay. So this is the basic design of HDFS. Okay. All right. So due to the time constraint, and this is more related to distributed computing instead of parallel computing. So we didn't discuss the detail of other, like how to ensure data consistency in this file system. We just give you an idea of what a distributed system looks like and how you can, provide reliability and how to avoid synchronization or communication. Okay, and one of the thing you can see is it partition the file into those big chunk. Okay, and usually this chunk is usually shouldn't be too small. The reason is if the chunk size is too small, you have to store more metadata, right? Because a file will be partitioned into more chunks, and every chunk require an entry in the metadata server. And every data, every chunk, every access to the chunk, you have to issue a query to the metadata server. So if you have too many chunks, you will have a lot of overhead. So that will, again, cause some performance degradation. Okay. On the other hand, because the chunk size is so large, so you can see this file system usually doesn't provide good performance for small data. Because if your data is too small, for example, smaller than 64 megabytes, then your data essentially is not partitioned at all, right? It will just store in one chunk. So you will only be stored on one location. So the parallelism for your I/O is limited by the chunk, right? More chunks you have, more bandwidth you could get from the file system. So you can see many benefit from this file system is contributed to large file. So small file, usually you will find the performance could be even worse than your local file system. Okay? So it is a very customized file system designed for big data, specifically for solving the volume challenge. Okay. Okay, so that's the brief introduction for HDFS, and for your homework, you also only need to implement the operation we mentioned here. You don't need to worry about anything about data replication or data recovery, any of those. So you don't even need a master. All you need is just to mimic the behavior of HDFS from your local file system. Okay, so we will announce the homework spec and provide some explanation of the spec on next Monday. So if you still have question about the homework spec, then you can feel free to ask question to me or the TA. Okay. All right. So now we will goes to the most important part of this lecture. So we are going to introduce MapReduce, right? So as I said, MapReduce is actually designed and implemented by Google, and later implemented as an open source, make public by the open source community. Okay, and so Hadoop become the other name of MapReduce, right? Specifically referring to the open source implementation of MapReduce. Okay, but besides represent the implementation of MapReduce, the MapReduce, this term also represent a programming model. Is similar like the divide and conquer programming model we introduced, but a bit more specific to this particular system. Okay, so MapReduce is also represent a programming model, a kind of a divide and conquer programming model. Okay, and it can also referring to as the system architecture, like the architecture we explained for HDFS, right? So MapReduce, it also is a client-server distributed system, and so when we talk about MapReduce, also imply it could also be used as when we as as how we to design or how we discuss a system architecture for parallel data processing. Okay, so you have many angle um, to look at this term, right? Just an implementation, or it's a programming model, or it's an architecture of a distributed computing or data processing solution. Okay. Okay, so we start with the programming model part. Okay, so what is the programming model of MapReduce? As I said, it's a form of divide and conquer. Okay, so why divide and conquer? Because you should know now that it is a model that can explore data pair reason, right? Is a model that simply by dividing our data to independent sub problem or sub data set and independent data set, and each of the data set can be processed by an individual worker. They can process the data in parallel, right, without any dependency. And then the result can be conquer, aggregate together to get our final result. So divide and conquer is if your algorithm can be implemented as a divide and conquer algorithm, then usually you can have a pretty good data pair reason, right? And you can explore the power of parallel computing. So it can achieve better performance and better scalability. Okay. All right. So MapReduce first follow the divide and conquer principle, and the second thing is he will basically divide the operation into function. Okay, so you will try to abstract the programming as function codes. Okay, so it's also called the functional programming. Okay, so the reason is now you can simplify the programming to just coding those functions, right? And so if we look at how a typical solution or demand from a big data problem usually consists of those 5 steps. First, partition the data into record, independent record, and then iterate it through those records. For each record, we try to extract the value or the information out of each of those records, right? And then try to aggregate the record by sorting or shuffle those intermediate results before we aggregate the result to get the final result. And of course, at the end, we will try to write the final result to the file. Okay? Because the data is so huge, so we cannot keep in the memory. We have to store in the file system again. Okay. All right. So it turns out, most of the time, when we try to pre-process the data or at the early stage of data processing, when we try to turn the raw data to the information, this is what we do. Okay. And in those 5 steps, you will see that step 1, the third step, the first step, the third step, and the final steps, they are not related to your problem solving. They are always the same, right? No, so there's no logic need to be decided by the programmer. What programmer needs to decide is the second step and the third step, right? And that's what we call the map and reduce, right? The map function that try to map a given record to some intermediate record with the value you want to extract. And the fourth step is to reduce those information to collect the result from all the records to become the final output. Okay? So it turns out for most of the application, or from the user side of point of view, all they need is to decide how to write the map function and the read and the reduce function. Okay. Okay, so that's why it's called a functional abstraction, right? We abstract the process into a set of functions. And you will find out that only the map function and the reduce function needs to be written and decided by the programmer. While the other three steps, the other three functions can be implemented by the framework and apply on, all the progress. Okay? And so that's where the name of map reduce comes from. Okay, because that implies the programmer only need to write the map function and the reduce function. Okay, all right. So to combine those two concepts together, right, the function abstraction and divide and conquer together, uh, then you have the map reduce programming model. Okay, so this programming model specifically referring to this process. Okay, first we will divide the data into set of record. Okay, and each record will be stored in the form of a key value pair. So this is the primitive data type in MapReduce programming. Okay, every record is a key value pair. Okay, because this is in terms of the data type for key and the value, that can still be right determined or defined by the programmer. But you need to have a key and you have to have a value. Okay, and the reason you have key and the value is because later on you will see when we do the aggregation, we will aggregate it on the key instead of just the value. Okay, all right. So anyway, every record can be represented like here, right? Key value. So you might have key one and value of V, right? And K2 as the key and V as the value. Okay, so you will have a set of key value pairs. Okay, and the map function, as like we said, the purpose of map function is to given input key value pair, it will convert it and output intermediate key value pair. Okay, and this mapping could be one to many or one to nothing. So you can see in this case, maybe a key value pair input record will output 2 or 3 intermediate records, while this map function apply on this record will generate nothing. Okay, so so basically you are converting the records. Okay, and you could also generate more records or filter data. Okay, all right. So after this is what we call the map phase, do the mapping. And after the mapping, we will try to group those records by their key. So you can see K1, if the value of a key is K1, then all those records will be collected together into a list. So a list of values, right? Because those records may have the same key, but they may have different values. So the records with the same key will be collected together and their value will be represented as a list of values. Same thing for any key we found from this process. Okay, so the reduce function will only apply on a key for each key. Okay, and it will only aggregate the values of the same key. Okay, so its output again is a key value pair, right? So this is what we call the map reduce programming model. Okay, this may not make sense to you at the moment, but let's look at the application, then you will see how we could apply this model to solve a problem. Okay. Okay, now we put this programming model into action. Okay, so the classic example is word count, right? Given a huge file with lots of words inside, what we want to do is to count how many words, right? How many words exist in this file? Okay, for example, given this input file, we want to generate this output file. Says you have bear twice, tar 3 times, etc. Okay, and what happened under this programming model is that you can see the first step is to divide the data, right? The input data set into record. And this is automatically done by the framework. And by default, it is done by partition the file by the new line break. Okay, so every line is a record. Okay, and the key usually is the line number, and all the text is the value of this record. Okay, so in this case, since we only have 3 lines, so it will become 3 input records. Okay, and each record, as we said, it will be fit into a map function. Okay, and so then it will depend on the map function you write, right? So in this case, you can see the map function says, as we said, no, document ID is the key, and the text is the value. Okay, so we don't care about the document ID or the line number. We only care about the value in this case. And what we did is we will iterate through the word in the text. And whenever we see a word, we emit, means we output intermediate key value pair. And the key of that record should be the word. And the value of that record should be 1, indicate we see this word once from this line, right? So after the map function, what we get is this, right? So we will, for example, this record will actually generate 3 intermediate key value pair. And their content is deer 1, bear 1, river 1, etc. Okay, so this is the result generated from the map phase. Okay, all right. So you can see in this case is every input, this 1 input record will actually generate 3 records. And of course, sometimes you can, if you want to filter, then you can generate nothing, right? This all depends on how you write the map function. Okay. All right. After the mapping phase, then the framework will do the shuffle. You don't need to define any logic because you always try to shuffle the records generated from those mapping functions, so that now the record with the same key will be put together, will group together, and it will sort those keys by default is according to their ASCII code. So it should be bear first, then car, then deer, then river. Okay. All right. And so after aggregated, we will now call the reduce function. And the reduce function will, remember, the input should be a key with list of values, right? So this whole group will given to the reduce function at once. And the implementation here, you can see, is again iterate through the values. And we simply just count how many values are there, right? And then emit the key, right? We keep the original key and output the aggregated value. So that gives us the result shown over here, right? So after the reduce function process this intermediate key value pairs, this group of intermediate key value pairs, it will generate bear 2, right? So on and so forth. Okay. All right. So as you can see, this is how we could follow the map reduce programming model to design and implement a word count algorithm. Okay. And as you can see here, as a programmer, all you need to do is define the map function, is to implement the map function and the reduce function. And you don't need to implement any code for splitting, shuffling, or output or input. And the reason for that is you can see for map function and reduce function, when you design and write the code, you don't need to worry about any synchronization or communication problem, right? You don't need to solve the problem as a parallel algorithm, right? Because you are limited by this function, the definition of this function. All you can do is to decide how you would like to convert a input record to a intermediate record, right? You don't care about how many records are there, or how you want to exchange the data between records. You are not allowed to do that. So it limits the the design of this function, and it's by purpose, right? It's because it separates the problem. So for programmer, you can only think and solve the problem under this context, and this is a context that is irrelevant to any synchronization and communication problem. Okay? Same thing for reduce, right? All you could do is to decide how you would like to aggregate the values, right? And so every key is handled independently. Okay, so you don't need to learn parallel programming in some way in order to write this map reduce code. Okay, but overall, you can see you still have to know this map reduce programming model, so you can come up with this solution, right? So it's not entirely true that you don't require any knowledge for parallel programming, but the code you write in map function and reduce function, they are independent. That's why the computation can be distributed on individual worker and processed individually, so without any synchronization and communication overhead. Okay, and for those part that require synchronization and communication, like shuffling, like splitting, like concurrent write, all those operations are handled by the framework. So you can see they separate the concern, and so that it supposedly can reduce the programming effort from the programmer. Okay. All right. So that's why you can see this kind of a solution is not just a library. They are a framework, or even we call it as an execution framework, because it managed the execution for the programmer. Okay. All right. So actually there are a lot of problems that need to be addressed by the framework. Just like the challenge you face in your homework 1 and homework 2, right? You have to do the load balancing in your homework 2, right? And you have to decide how to distribute the data in your homework 1. You have to handle synchronization problem for all the homework you did. So you can see all those problems needs to be solved, but they are solved by the framework, not by the programmer. Okay. And for distributed computing, it's even more complex because you have to handle value. And this is also handled by the framework, not by the programmer. Okay. So that's why we need a execution framework to separate the concern and solve those problem by the framework, and leave the programming problem to the programmer. Okay. All right. So we will talk about how MapReduce, the master of MapReduce, address those issues later on. Okay. But first, you need to note that if you can record, we said MapReduce should be run with HDFS, right? They could run separately, but usually they run together. And why is that? Because it is a very important design from us for the system point of view. Because in the past, for example, in the parallel computing cluster you are using in our class right now, you can see the compute node and the storage node are separate. The storage node is your network file system, maybe stored on the head node, right? Or a separate servers. And compute node only try to do the computation. When you do the computation, you have to pull the data out from the storage node. So there's a network transfer. Okay, this is a good design for a system like supercomputing, because if you separate two systems, then you can customize them, right? So this system is optimized for storage, and this system is optimized for computing. So for example, you might have a better and a larger storage device installed on this server, while you might have more memory installed on the compute nodes. So that's how you can have better performance. But the problem for this system design is you have to, right, transfer the data from one node to another. So it requires a very high network bandwidth, right? As a matter of fact, you suffer from this problem in our class, in the cluster of our class, right? Because we didn't optimize the network here. So when many people try to access the data from the file system, you suffer from the I/O bottleneck, right? So you can see that if you have the problem become more, become worse when you have a larger volume of data, for sure, right? And so for big data problem, this is not a good solution, because you will require a huge amount of network bandwidth at the same time. So the cost will be very high. Okay? All right. So how Hadoop solve the problem? They put those two systems together. Okay. So in the other words, that means any server that install the MapReduce or Hadoop system, you will also install the HDFS file system. So the node will store the data as well as processing the data. So that gives you a chance that the data you try to process is already stored in your local file system. So when you try to access the data, you don't require network bandwidth. Okay. Therefore, now you can realize the idea of moving process to data instead of saying moving data to the process. Okay, because data is expensive, it's hard to move. It requires network bandwidth to move it. So for a Hadoop solution or MapReduce platform, what happened is the scheduler will first check where the data is stored and then dispatch the process to the node with the data. So he can process the local data without using network bandwidth. Okay? So that's why we said usually MapReduce is stored with HDFS. Okay, if you store the data in a remote location, then MapReduce still could retrieve the data from that remote location, but it usually require high network bandwidth. So you may suffer from that. Okay. Okay, so that is why those solutions are built on top of each other. Okay. So this is what I mentioned. You can see that this is a physical node. Okay, and on this physical node, we will install task tracker and the data node daemon. The task tracker and the job tracker, the job tracker is the server for MapReduce, and task tracker is the worker of MapReduce. The NAND node is the master for HDFS, and the data node is the worker for the HDFS. Okay, so a server, any node, plays the role for storing data and processing the data. Okay, and job tracker will talk to NAND node. So when the job try to process some data set, it will know where the data is located and submit the job, the data processing job, to that node. So the task tracker can access the data in its local disk. Okay. All right. So that's the whole view of the whole platform. Okay. Combining storage and processing. Okay. All right. So that's it for today's class. And next time we will take you through, use example to take you through how the work on example will actually happen on those storage system and data processing system. Okay, so you will see how MapReduce in action on those server. Okay, all right. Any questions?
可以问那个，就是自己